Right.
All right, so we're here. So what I'm going to do here is, since we just had our test on chapter 11, I think what we will do tonight is get as far as we can into chapter 13. We are running out of time, as you know. I think if I look at our schedule, today's the 21st, next week's the 28th. I think that although technically we could have the final on the 19th, I think we already agreed that we should try to get it out of the way on the 12th. And in order to do that, we really have to get as far as we can into 13 as we can tonight. So it's a very interesting chapter, although it's a little bit different because we have to introduce a brand new probability distribution, and one that we haven't seen before. And one which, by the way, the calculator can help us to a certain degree, but there are certain things that it can't do. And so because of that, we're going to need to use a table for certain applications. Yeah, I know. You figure after a while the calculator can do everything, but not necessarily. So let me open up the chi-square table real fast and add it to the group here. Oh, there it is. And so here it is. So what we're going to do is start by introducing the chi-square distribution, and then it turns out the chapter is broken up into three pieces: 13A, B, and C. Each one is about a different application of the chi-square distribution. So when we're done, we'll have three of them completely finished, and we'll be ready for whatever comes next. But I do want to mention one important detail here. In order to get through the material in chapter 13b, we will have to calculate probabilities based on the normal distribution as well as the Poisson, which you haven't probably thought about since the spring. So that's going to take a little.
I don't know what's going on, bro. He has like 10 tabs open. This is freaking out. Like,
okay. Anyway, one other thing: be careful. If you should have your microphone muted for the time being. If you want to ask questions, that's fine. You should open it up and ask questions. But if you have the microphones on, then we'll hear any background noise that's going on. And so we don't want that. In fact, during the COVID, when all we had was online classes, very occasionally somebody would start talking without realizing their microphone was on. And let's just say that they would say things that they wish they hadn't. So we don't want any of that tonight. But even more importantly, we just don't want the background noise. So I'll mute anybody who forgets. But if you do have a question, you can feel free to turn it on, or either that or just type it into the chat room, because I'll see that too. All right, so hopefully you have your calculators in front of you. And we'll start with 13A. And by the way, these are all posted in Blackboard, so you can go look at them and download them even now if you want to. So first things first, this chapter, as you can see, is called the chi-square application, which means we're introducing a brand new probability distribution called the chi-square distribution. And the entire chapter is this distribution plus three applications of it. So first things first, up to this point, all we've seen as far as continuous distributions are concerned is the normal and the t. And they have a lot in common with each other. The chi-square is the first one that's really significantly different. In fact, let's just go through the list of properties of the chi-square distribution. The most important things are that, first of all, it is a continuous distribution, just like the t and the norm. Where it really starts to deviate from the other two is that it's not symmetrical about the mean, number one. And number two, it is undefined from negative values. Now, it just so happens that I have a graph here that shows you what it looks like. Like the normal distribution, I'm sorry, the t, it is characterized by degrees of freedom. So when I show you this chart, what I want you to note here is that I've got four different versions of the chi-square distribution here. And in each case, what is different is the number of degrees of freedom. So for example, up here, you'll notice that with 5 degrees of freedom, the curve is skewed to the right. In other words, it has a long right tail. And if you look carefully at the axis, you'll see that the values actually start at 0. This function is not defined for negative values. So it's not only not symmetrical, but it only is defined for positive values, which is very different than the normal and the t. As I start to increase the number of degrees of freedom, though, if you notice, like here with 10, it starts to shift to the right just a little bit. With 20, it shifts even further, and it's actually starting to look a little bit like the normal distribution. It's not actually symmetrical, but it's getting there. It's getting closer. And with 30 degrees of freedom, it starts to look a lot more like the normal distribution that we're used to. But in none of these cases will you see any negative numbers. This distribution is only defined for positive numbers. And that is one of the most important differences between chi-square and the t and the standard normal. Also, again, like I said before, like the t distribution, it is characterized by degrees of freedom, but it is not symmetrical. So it has a lot of useful applications, and we save it for certain specialized cases, like the ones we'll be looking at tonight. Now, also, we're going to learn about a brand new Greek letter. Hold on one second. Now, you're probably wondering, how am I going to write on the slides? Well, I happen to have a tablet here, a very nice tablet, which lets me write directly on the screen. So I'm going to do that right now. You'll see. This is the Greek. Oh, man, what's going on? There it is. This is the Greek letter nu. Okay, now, I don't think we've seen this before. And so this represents the degrees of freedom. Or the chi-square, and later on you'll see for any other distributions that we introduce, chi-square and maybe some of the later ones, the letter nu is used to represent the degrees of freedom. Now, with the t distribution, the degrees of freedom was typically related to the sample size that we were using. Here it's a little bit different. Although it often is related to the sample size, it can be calculated in other ways as well. Now, what's going on down here? You remember Z is the standard normal random variable. Okay, we reserve Z for the standard normal case, which is the one where mean is 0 and the standard deviation is 1. Okay, so we haven't forgotten that, but what I wanted to do is point out that what you're seeing here is we have taken a series of these standard normal random variables, we've squared them and added them up, and the sum is our chi-square random variable. And this is why the chi-square distribution cannot be defined for negative values, because we're adding up squared numbers, which are each individually guaranteed to be either 0 or positive. And one last detail, the number of terms that we add up defines the degrees of freedom. Okay, so in other words, if nu is 10, that means we're adding up 10 of these standard normal random variables. That means we have 10 degrees of freedom. Okay, so that's what this is all about. So this is not something that's critically important. We do need to understand what's happening here, but what we really need to know is that the chi-square distribution does not allow for negatives. Now, and yes, and we've already seen the graphs, so we have a feel for what this distribution looks like. Now, the next thing we want to do is define the moments of this distribution. Now, the moments would be, for example, the expected value, the variance, and the standard deviation. Every distribution has its own unique set of moments. So here, it turns out that the expected value, the chi-square random variable, is just equal to the number of degrees of freedom, or the letter nu. The variance is just 2 times nu. And that, of course, means that the standard deviation must simply be the square root of 2 times nu. So these are easy to remember. Now, And the final exam, unlike the second midterm where we just had 5 huge problems, there's a very real possibility that we're going to have some fill-in questions. And if we do, there's a very real probability that these will be included among those fill-in questions. So I just want to mention that right up front. The second midterm was a bit unusual. It sort of fell into us from necessity to have it that way. But for the final, there's still a chance that we may have those fill-in questions. And you can see these would make very nice fill-in questions. All right. So anyway. Now, by the way, what applications are we going to be using here? Well, there's several we could choose from, but one thing we're going to do is we're going to test hypotheses about the population variance. This is something we haven't been able to do before. Every time before, when we tested hypotheses, they either had something to do with the mean or possibly the proportion of a population. Now, with this new distribution, for the first time, we can test hypotheses about the variance of a population. Another interesting test is this one. This is something we haven't seen before. It's called a goodness of fit test. What exactly is this all about? What we're trying to find out is if our population follows a specific probability distribution. For example, what if I have a bunch of data and I want to know if the underlying population is normal? Oh, that's an interesting question. Up to this point, we've never done anything like this. Now, you may wonder, why do we need to do this? It turns out a lot of statistical tests that we use are based on the assumption that our data are normal. And if they're not, that means our results will be very, let's say, questionable. So it's not unusual for us to test hypotheses about the normality of the population from which our data are taken. That's what this is for. We want to show, yes or no, are the data really normal or not? It's sometimes really important to know this. Okay. Other times, not so much. It's less of a problem. It may just be that as long as the data is close to being normal, it's fine. But for some cases, it's really important to make sure. And so if that's the case, we can go ahead and use one of these goodness of fit tests to prove whether the data are normal or not. All right. Well, let's start. Let's start with the first case, testing hypotheses about a population variance. Now, this is the one where we will need the chi-square tables. The calculator really can't help us too much with this one. So what we're going to do is test hypotheses about a population's variance in the following way. We start with a null hypothesis, as we always do. And you notice that the way it's written, we want to find out if our population variance is equal to some specified constant. Yes or no? All right. So we've seen this approach before, except in the past, we were dealing typically with the mean. Now, suddenly, we're finding ourselves testing the hypothesis about the variance. Then, once we've written down the null hypothesis, as is so often the case, we have 3 alternatives to choose from. We've got a two-tailed, right-tailed, and two-tailed test, and they're exactly the way you would expect them to be written. The two-tailed test means that the two are not equal to each other. The right-tailed test means that the sigma squared is greater than this constant, and the left-tailed test means that the sigma squared is less than this constant. So these are just perfectly consistent with what we've done in the past, except with the variance instead of the mean. Now, here's where it really starts to get different. What really separates one hypothesis test from another is the identity of the test statistic. That's really what is very different from one case to the next. Now, it just so happens in this case, the test statistic is very, very straightforward. That's not always true. Okay, we're going to see later on some cases where the test statistic is actually kind of frightening to look at. Okay, but this one is very down to earth. So let me show it to you, and we'll see what it means. Here we go. So this is our, by the way, I think I forgot to mention, this is the Greek letter chi. Now, in spite of the way it's spelled, it's pronounced chi, like Ki, let's say. I don't know how or why this happened. Why do we insist on spelling it CHI if we're going to pronounce it chi? But there it is. So, actually, hold on one second. This is the letter chi, just this part. This then becomes chi square. And by the way, this chi actually is the Greek equivalent of X in the Roman alphabet. And you can tell just by looking at it. Anyway, so these other terms we're very familiar with. This is our hypothesized value of the sigma, or the variance rather. And you can tell because of that zero subscript that always has meant in the past the hypothesized value of something. The S is our sample standard deviation. And then N is the sample size. So nothing has really changed here. Here's another twist. Because the chi-square distribution does not have negative values, and because it is not symmetrical, the critical values will be just a little bit more challenging to calculate, especially because we can't look them up in our calculators. For these, we have to use a table, and we have to know how to do it properly. So let's take a look at these. Let's start with a simple case. Just because it'll be easier, let's start with a right-tailed case. All right, what's going on here? All right, well, let me draw a little sketch. Oh, what's going on here? Oh, there it goes. Okay. All right, so for this first, we're going to start with the right-tailed test, just because it's the simplest case. And then we'll work our way up to the more complicated ones. Now, here's an interesting side note. Remember when we had the t distribution, we would always write the test, the critical values, something like this. Let's say it's a right-tailed test. You would have the numerator, or the superscript, I should say, is your degrees of freedom. The subscript is the alpha, the tail area. Well, with the chi-square distribution, the superscript is already taken by that too. So we have to write two things in the subscript. We usually write alpha, or whatever the tail area is here, and then we follow that with the degrees of freedom. So whatever our degrees of freedom are, we know that there's alpha in the right tail. Okay. Now in the slides, it's simply referring to this as chi-squared alpha because we don't know what the degrees of freedom are, but it means the same thing. So the point of it is that alpha, whatever it is, and we know that it usually is 0.05, is in the right tail. But how do we look it up? All right, so this is where the table comes in. Suppose the degrees of freedom is 10 and alpha is 0.05. Then chi-square 0.05 comma 10 is found in our table, and this is how we look it up. This table, by the way, is different from the others because these areas in the top represent the right tail of the distribution. Usually it's the left tail, but for this, it's the right tail. Oh, I forgot. This is a PDF. I can't actually write. Oh, there we go. So what I actually need is to find 5% that goes in the right tail and 10 degrees of freedom from over here. All right, you see up here, DF means degrees of freedom. 5% is in the right tail. Where we combine these, it's 18.307. That's how we look them up in this table. So for this one, the critical value will be 18.307. I'm just making sure I didn't goof it up. Yeah, that's it. So in other words, if the test statistic is greater than 18.307, we'll reject the null. Okay, otherwise we won't. Now, what about the left tail? Interesting. Let's keep the same numbers. Now, with the t or the standard normal, due to the symmetry of the distribution, the left tail would have a negative critical value, which is equal to the right tail critical value. Here, that's not going to happen. So what do we do instead? All right, let's find out. So the way we have to think about it is that we'll have alpha in the left tail. Let's continue to assume that alpha is 0.05 and that we have 10 degrees of freedom. But the table is geared towards the right tail. So the entire area in the right tail is 1 minus alpha, which is 0.95. So that means here we have not 0.05, but 95. And then we combine that with 10 degrees of freedom. Okay, so that was the tricky part. Instead of having the negative of whatever the critical value was for the right tail test, we have to have a separate version basically for the left tail, based on the idea that for a left tail area of 5%, that implies a right tail area of 95%. And that is where we're going to get our critical value. So we go back to the table. And now we look in this column, because 95% is in the right tail, so that 5% can be in the left tail. And then we end up with 3.94. That is our critical value. Anything smaller than that means we'll reject the null. Oh, before we continue, I forgot to mention a couple things. First of all, this is being recorded, and I will make it available on both Blackboard and my own personal YouTube page, just in case there's an issue with the Blackboard. Sometimes, because these are fairly bulky files, there can be issues. So here's my YouTube page. And you can see it's bursting at the seams with recordings from past classes. And so I'll just add it in there if you want to look at it. And if you don't, that's okay, since you were here tonight. But also what you're seeing right here, the slides where I'm actually writing on them, I will post them on Blackboard as well. So in other words, all these handwritten notes you'll have available to you on Blackboard. Okay. All right. Anyway, so now what this means then is that you look at this table, the right tail test, the critical value is chi-squared alpha. The left tail test, it's chi-squared 1 minus alpha. So having seen an example, I think it's easier to understand what that's supposed to mean. It doesn't specify the degrees of freedom because we don't know what they are, and it doesn't actually matter what they are. None of this would change. So remember here, the alpha is in the right tail. Here, the alpha is in the left tail, which means the right tail is 1 minus alpha. All right. And then, of course, we have the two-tailed test. Let's look at that one. So again, let's assume alpha is 0.05, degrees of freedom is 10. So we have 5% that has to be split up between the two tails. So here's how it's going to work. Of alpha will be in either tail. Okay, in other words, alpha is the total value or the total amount of area in the rejection region. So we split it up. The 2.5% is in the right tail, and 2.5% is also in the left tail. How do we find these in the table, though? Well, for this one on the right, two and a half percent is in the right with 10 degrees of freedom. But what about this one? If 2.5% is in the left tail, all of this is the right tail, 0.975, which is equal to 1 minus alpha over 2. So those are our two critical values. We'll look them up. Oh, sorry, I wrote the wrong thing here. Wait a minute, my mistake. This should have been 975. Sorry about that. So we're going to look those up right now. Chi-square 0.975 with 10 degrees of freedom equals. Okay, we go to the top. Here we are, right here. Oh no, what did I do? Okay, that's better. Along with 10 degrees of freedom, that's 3.247. Right tail of this critical, the right critical value should say, go here. We now need 2.5% in the right tail combined with 10 degrees of freedom. That brings us to 20.483. Those are our two critical values for a two-tailed test where alpha is 0.05 with 10 degrees of freedom. Those are the two tails that we need. And if you look at the slide, you'll now maybe understand a little better why it's written this way. Okay, so before it looked very abstract, and you might have said, what's going on here? But now I think it's easier to figure out what this means. All it means is what's going on in the right tail. And that's where these are coming from. Wow, that was intense. But all of this because we don't have symmetry and we don't have negative numbers anymore. It does make things a little bit messier. Oh, but what can you do, you know? Also, it would be nice if the calculator had this function built into it. I mean, remember we used INV norm for the critical values taken from the normal distribution and INVT for the critical values drawn from the t distribution. We don't have the equivalent formula for chi-square. Okay, if you're upset, write to Texas Instruments and complain about it. But instead, we use the old-fashioned approach, which is tables. Well, with all that being said, we have to then make a decision. The one thing I do want to mention here, which I think I forgot to tell you before, is that for the examples, I gave you 10 for the degrees of freedom, but for this application, the degrees of freedom is very simply equal to n-1. Okay, so for problems where you're looking at the variance of a population, your critical values will be based on n-1 degrees of freedom. All right, finally, we're ready for an example. So we're going to be looking at stocks right now. Now, I don't know if you've had your first finance course or not, but the way we judge a stock is by looking at its rate of return, which is a percentage of some kind. But the way we measure the risk of a stock is with its standard deviation. Okay, and so here we've got an investor who picks a sample of 30 stocks from his portfolio, and he discovers that the sample standard deviation is 0.23 or 23%. That is a measure of risk. The higher this number, which is often referred to as volatility in the financial markets, the riskier the stocks are. Now, this investor is worried that his portfolio is too safe. He wants to know if the standard deviation of his portfolio, the entire portfolio that is less than 25%. So what we're going to do here is write out our hypotheses, not in terms of standard deviations, but in terms of variances. How do we do that? We're going to square the standard deviations. Okay, so here's what we're going to do. First of all, the null, which could be written as the standard deviation is 0.25, is equivalent to saying the variance is 0.0625 because 0.25 squared is 0.0625. Now, it's a left-tail test. The investor is looking for evidence that the standard deviation is less than 25%. We have to assume here that if that's the case, he's planning on selling some of his safer stocks. So here we'll write the alternative as sigma squared is less than 0.0625. So the standard deviations are converted into variances. This is our null and our alternative hypothesis. So clearly it's a left-tail test. We're just going to assume that the alpha is 0.05. And so now we're going to calculate our test statistic. By the way, I forgot to, I kind of glossed over this. He did take a sample of 30 stocks. And he discovered that the sample standard deviation is 0.23. Okay, that's all we need to know to figure out this test statistic. So let's plug in those numbers. Keeping in mind that the hypothesized variance is that 0.0625 that we found earlier. Yeah, 0.0625. So if you plug those in, you'll get your test statistic. So with all that, you'll end up with approximately 24.55. Now, you'll recall that when we were using the normal and the t-distributions, the test statistic rarely went above, let's say, 4 or 5, positive or negative. This one is 24.55. So you might be saying to yourself, you know, that's a pretty high number. Maybe we did something wrong. That's not the case because the chi-square distribution is derived from squared terms. the values, the chi-square distribution are typically quite a bit larger than with the standard normal and the t. In fact, if you look at these axes, you'll see down here in the bottom right-hand corner, for example, the number you see here is 55. It's not that unusual for the chi-square random variable to have very large numbers. In fact, if you look at our table, if you go down far enough, you see eventually it goes over 100. So with the chi-square distribution, the values that we will get are typically quite higher than what you would expect to see with the normal and the standard, the standard normal and the t. So don't be put off by that. Don't assume you made a mistake, because you probably haven't. Anyway, so once we have our test statistic, now it's time to find our critical value. Well, again, with this one, it's a left-tailed test. So whatever it is, we're going to have alpha in the left tail. And then the degrees of freedom is just simply n minus 1. Or in other words, well, I'm sorry, I wrote the wrong thing here. This should have been 1 minus alpha because it's in the left tail. Hold on one second. Because alpha is going in the left tail, but the table requires us to tell it the right tail, which would be 1 minus alpha in here. So we're going to have 0.95. And n minus 1 is 29 because our sample size was 30. So we need to go to the table and look for the combination of 95% in the right tail and 29 degrees of freedom. So let's go find it. I don't know if I can erase these or not. I guess it's okay. We'll find it. It's starting to get a little cluttered though. 95% combined with 29 degrees of freedom. That's this column. And 29 degrees of freedom brings us to 17.708. Okay, so that is our critical value. So if the test statistic is less than that, draw another one down here. This is our rejection region. And as an area 0.05. But remember, our test statistic was 24.55, which is not in the rejection region. Therefore, we do not reject the null. Okay. And that's it. So what that means is that the investor will not change his portfolio. Because there's no evidence to suggest that the variance is below 0.0625, or the equivalent of saying that the standard deviation is not below 0.25. All right, so this is how we test hypotheses about a population variance. It's a very straightforward case. I think you'll agree. It's very similar to what we did in previous chapters, and except that we have a different table to deal with. I mean, that, and also, there's some complexity here with the way we calculate the critical values, but basically, once you get used to that, you'll see that it's not a problem. And plus, by the way, we will have problem sets to work on where we get plenty of practice with this. Okay, so this is not just the last time you'll be seeing this. So just remember, we have our normal, null, and alternative hypotheses based on the variance. Of course, we're given a level of significance. This is our test statistic, which is easy. But like I said, the critical values are a little challenging. But as long as we use the table carefully, we can find it very easily. And then we can make a normal decision, which means if the if the test statistic fails to fall into the rejection region as it did here, we do not reject the null. By the way, I do want to mention, you might be wondering, well, when are we going to figure out the p-value? We did a lot of that in the last section. Again, the calculator doesn't have the right functionality to do this. So for this case, at least, we will not be using the p-values. Okay. I know it's disappointing, but for this case, we're going to stick with the traditional approach by simply comparing the test statistic with the critical value. All right. Now we're ready for part B. This is a very interesting topic, but it is very complicated. So we're introducing the so-called goodness of fit tests. And again, the reason why this is so important is because we often need to make sure that a population is indeed normally distributed, because a lot of the tests that we use depend on the assumption of normality. And if we do not have the ability to prove that that's true, we might run into trouble. So this is a formal way of demonstrating whether our population is normal or not. So how do we do this? For this one, we have to do a lot of work, but the calculator can also be very helpful too. So this is sort of a mixture of sort of a complicated process where the calculator can semi help us out. So first things first, how do we state the null and the alternative hypotheses? Suppose that we're interested in comparing a population of data to the normal distribution. Well, then there's only one way to write the null and the alternative hypotheses. The null is that the population is normal. The alternative is that it's not. That's all we have to choose from. Yes or no. Which implies that this test is always carried out as a right-tailed test. We don't have, there is no such thing as a left or two-tailed test with goodness of fit. It's always right-tailed. That makes things a little easier because it's one less decision we have to worry about. All right, so now here's where the fun begins, the test statistic. The test statistic is pretty challenging. But let's think about the logic behind it. What exactly are we trying to do? All right, let me just briefly show you what the test statistic is all about. With this type of test, we will be given a set of observed values or frequencies. Okay. We will be asked to compute the frequencies that would take place with a specified probability distribution. These are known as the expected frequencies. Okay, so we'll have two sets of data. The ones that are given to us, the ones that are actually observed, and the ones that you would see if the data really followed the particular distribution you're looking at. So what the test statistic does is it compares the two of them. And it compares observed and expected frequencies. The closer they are to each other, the less likely we are to reject the null hypothesis. Okay, so that's kind of the point of all of this. We want to see how close they are to each other. You could easily imagine, imagine if I had, let's say, data. Let me see if I can draw a proper graph of this. Let's say that you have data which you think is drawn from the normal distribution. What's that? So this is a special type of graph called a histogram, where the results are put into categories. This is the normal. You can see it looks just like the normal curve. So imagine that instead, here's your data. And remember, the null hypothesis is that the data are normal. What if your data looks like this? All right, so now I'm drawing it very badly. Let me try that again. Well, that's not that bad. I mean, it's not that far off. The question is this close enough to the normal distribution to avoid rejecting the null hypothesis? Well, we can't tell until we run the actual test. Okay, so that's the whole idea. We've got actual data. By the way, these would be the so-called expected frequencies. These would be referred to as the observed frequencies, meaning this is the actual data. So what do you think? Are they close enough? I don't know. It's hard to say. They're not perfect. They're not terrible. So we need to find out with our test statistic whether or not the observed data is close enough to the normal data to avoid rejecting the null. Okay. So that's what we're going to find out. So let's start with an example. I think this would be the easiest way to go. We're going to start actually with the Poisson distribution. We'll want to be comfortable with both. We want to be able to compare data to the Poisson distribution and the normal distribution. So we'll start with the Poisson. So we want to know if the number of phone calls that we receive every hour on our cell phone follows the Poisson distribution. So we take a sample of 75 hours, and then we record how many phone calls there were in every hour. These are the results. So during that time, there were no calls 29 times, one call 23 times, two calls 17 times, and three calls 6 times. There were no cases with 4 or more calls. So these were observed frequencies. If you wanted to draw a little histogram, you could certainly do so. And I mean, it's a little awkward with this tiny little graph, but we can do it. So we get a 0 29 times. We got a 1 23 times. We got a 2 17 times. And we got a 3 6 times. Now, I don't happen to know off the top of my head what it should look like, but this is what our observed data looks like. What we're going to have to do now is figure out the so-called expected frequencies, which means what would these things look like, these categories look like, if this was really the Poisson distribution. Oh my God, yes. So it's been a while since you worked with the Poisson distribution, so I'll remind you how to do this on your calculator. But there's one holdup here. If you recall the Poisson distribution, let me just quickly remind you what that looks like. Now, I know you have this in Stats 1, but let's just quickly remind ourselves what this is all about. This is used for cases when we are observed number of events that occur per unit of time. So let's say we needed to know, understand the probability of getting, let's say, 5 customers using the ATM at a bank every hour. That would be something we would use the Poisson for. In other words, what's the probability that over the next hour, 5 people show up and use the ATM? Because we're looking at how many people, or the event is using the ATM, and time is an hour. So the way it works is, oh my God, what is going on here? What are all those weird symbols there? Well, let's remind ourselves what these terms all represent. Well, first, let me give you a chance to catch up, and then I'll remind you what these terms represent and also how to do this on your calculator. All right, so first things first, E is a constant. It's approximately 2.71828. You have an E to the X button on your TI-84. I'll get to that in a second, but now this is the Greek letter lambda, which is the average number of events per unit of time. Now, how about this X with an exclamation point? That's pronounced X factorial. You also have this on your calculator. All right, let's jump out to the next slide and see how this works on the calculator. So let's start with this one. Suppose you need to know the value of e to the minus 2 power. So here's what you have to do. You're going to type second. The button is labeled ln per natural log. And then you'll notice it has this e with a little box here. you're going to type -2, enter. Okay, -2, enter, and you'll come back with approximately 0.1353. Okay. And if you want to know the value of E, just E, you would do the same thing with 1. Okay. So second log, 1, enter, and you'll see it's exactly what I said before. It's approximately 2.718281828. And it goes on and on forever. Okay. Now, what about this factorial thing? This is a special mathematical operator. And here's how it works. It's only defined for non-negative integers. In the following way. Zero factorial is 1. 1 factorial is 1. But then it starts to get very interesting. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. Etc., etc. Now, how do you find this in your calculator? It's a little messy because it involves going through some menus. Right? So let's try that. Let's assume that for some reason we need to know the value of 8 factorial. How would we do that? All right, let's see. Oops, let me just leave it there for a second. Now, of course, it's possible you still remember all this very well, but I just want to make sure everyone's on the same page. So for 8 factorial, here's what you would do on this calculator. Eight. Now, you may not have ever seen this button there before. It's called math. And then you find the submenu prob. And then you scroll down to number 4. Oh, that's right. That's the factorial operator. Then you'll hit enter twice. Right, let's do that. And you should get 40,320. All right, now, suppose that we have a specific problem that we need to calculate. We can do one of two things. Well, let's do a quick example. Let's say that suppose that we know from experience that on average, 5 ships sail under the Brooklyn Bridge every hour. Okay, what is the probability that during the next hour there will be four ships sailing under the Brooklyn Bridge? Okay, so we know that this is a Poisson problem because it involves events taking place every hour. Specifically, ships go under the bridge every hour. So this is a Poisson. Oh, actually, hold on. Let me just leave it there for a minute so you can catch up. And then we'll figure out how to do this with our formula. Okay. Of course, the real problem with being online is I have no idea if you're behind or not. I can't see what you're doing. So if you're getting behind, or if you need to see a slide again, you can just let me know. Nope, doesn't look like. There's a mechanism here where you can raise your hand, but I don't remember how it works. You can just type whatever you want in the chat box or just turn on your microphone. All right, here we go. So because we're told that 5 ships sail into the Brooklyn Bridge every hour, lambda, which I can actually watch this. If you ever wondered how to do this on Word, there's this huge symbol box here, which has all these wonderful terms you might need. Equals 5 because we are told that the average number of ships per hour is 5. X equals 4 because we want to know the probability of 4 ships sailing under the bridge over the coming hour. All right, so that means we have let me just quickly write in the formula one more time. So e to the minus, remember, lambda is 5. E to the minus 5, 5 to the 4th power divided by 4 factorial. Okay, so go to your calculator and calculate e to the minus 5, as I showed you before. Second log negative 5 is 0.0067. 5 to the 4th is about, it's exactly 625. And 4 factorial is 24, as we saw a few minutes ago. And that's going to give us approximately 0.1745, let's say. Now, that wasn't that difficult, but it turns out that the calculator can speed things up for us even further. You probably are going to be annoyed when you see this because, I made you do all this work, but it's important to understand what these functions are doing, especially because we're going to use this quite extensively in a few minutes. So let's go look at what the calculator offers us. So besides using the actual formula, we can use one of the calculator's built-in functions. And how would that work? Well, remember in the past, we've used functions like normal CDF and to come up with probabilities. Well, this is a similar setup. So instead, this can be calculated with the TI-84 as follows. We're going to hit second bars, and then you're going to go down the list and choose. Let's see, where's it? D. Mine is D. It might not be D on yours, but it's spelled Poisson PDF. Make sure it's PDF and not CDF. Okay, so when you choose it, what is it going to ask you for? Oh, it's right there. Remember, we already told it lambda is 5. It needs the x value, which is 4. And then that's all you need. Now, at the bottom, you hit this paste button. And what you're going to get is 0.1755. Now, that's slightly different because of rounding. It's the only reason they're not identical to each other. Here, e to the minus fifth is not exactly 0.0067. That got rounded. But other than that, they're the same. So you see, this has been here all that time, whether you knew it or not. So that's going to help us now because we have to calculate several Poisson probabilities. So in order to test whether or not our data follow the Poisson distribution, we need to be ready to calculate Poisson probabilities. So first things first, what are the null and the alternative hypotheses? Well, the null is that the population follows the Poisson distribution. The alternative is that it does not. So if you notice, once again, that implies that this is a right tail test. The test statistic, now when you see it, don't panic. It looks scary, but it's not. What they're asking you to do is this, yeah. What's happening is that, remember, you have observed frequencies which are given to you, and you have expected frequencies which you will be calculating. Let's just say that I'll just make up a few numbers. These are 0, 1, 2. And you're actually getting 3, 5, and 1. So these O's are the expected frequencies. This is O1. This is O2. And this is O3. Actually, let me leave myself just a little more room here. This would be what we mean by O1, O2, O3. This is E1, E2, and E3. Okay, and so you fill these in. And that's your test statistic. Wow, that looks like a lot of work, doesn't it? Well, it is. But you'll see that the calculator can at least do some of it for us. Okay. So really all the work will go into the expected frequencies based on, in this case, the Poisson distribution. So now there's one more complication with this particular problem. If you notice, there's no mention here anywhere of the lambda. If that happens, we have to calculate it ourselves. Yeah, just what we needed, more work. How do we do that? Well, what I'm going to do is go back and copy the data we have into the next slide. All right, let's see what we can do. Oh, that'll fit. So I'm going to shrink it up a lot. I guess the, okay, hold on a second. Yeah, there we go. Oh, that's even better. Okay. What exactly happened here? Well, keep in mind that we have 75 observations in our data set. So what you're doing here is you're multiplying the number of calls. You see, you have 0, 1, and 2, and 3, by the number of times that happened, 29, 23, 17, and 6. And then turns out that adds up to 75. In the denominator, we just add these up. And so that gives me a 1, and that becomes my lambda. So it's not that difficult, it's just time consuming. So what that means is that for this particular data set, we can assume that our lambda is equal to 1. Huh. Now we can calculate any probabilities that we need for our expected frequencies. Okay, let's do that. Now, what I'd like to do here is I've got this chart here with Poisson probabilities, and I just want to show you one or two of them, and then we'll just fill in the rest. So using the technique I just showed you, here we've got the actual formulas, but if you use your calculator, for this first one, you would tell it the lambda is 1 and the x value is 0. Okay, so assuming you're in Poisson PDF, if you go down there and ask for Poisson PDF and you tell it that lambda is 1 and the x value is 0, you'll get approximately 0.3679. That's this one. For the second one, you would do the same thing, except now this is 1. Well, what do you know? It's the same thing. Wait a minute. I'm sorry. This is not correct. The lambda doesn't change. This should be a 1. It's the x value that changes. That's this one. And then for this one, oh, I did it again. Lambda is 1. X value is now 2. Plug that in. And you'll get this time approximately 0.1839. And then for 3, you'll get instead 0.0613. So in other words, obviously the calculator is giving us the same results as if we'd used the formulas themselves, and it's a little bit quicker. Okay, now here's the fun part. What do we do with these? Well, what we're trying to do is calculate expected frequencies. Right? So I'll give you a minute to catch up, and then I'll show you how this is done. So the surprising part here, well, maybe not surprising, is that we don't expected frequencies require us to know the probabilities, but we also will have to do the following. We're going to take each of the probabilities that we just calculated, and in each case, multiply by the sample size. Remember, there were 75 elements in the sample. So if you work through this, you'll see that by multiplying by 75, my expected frequencies are for 0, 27.59, again for 1, 27.59, for 2, 13.79, and for 3, 4.60. Okay, fine. So in other words, what this is saying is that if there's really Poisson data, those are the numbers you would get in each of those categories. So how do they stack up with the ones that we actually got? Well, what I'm going to do is copy these into the same table so you can see them all together in one place. And you can see where this is going. These are the observed frequencies. These are the expected frequencies. Are they close enough to conclude that our data follow the Poisson distribution? Yes or no? Now, here we can use the test statistic directly, but I think you'll find it's quicker and easier to use the calculator's capabilities. So here's what we're going to do. We're going to enter the data into lists. We'll use list 1 for the observed frequencies and list 2 for the expected frequencies. Now, how do you enter data into the calculator's lists? Let me remind you. First, go to stat. If you hit the stat button, then just hit enter. And you'll see lists across the top there. You see how you've got L1, L2, et cetera, et cetera. What you're going to do is go to the top, row of L1, and enter observed frequencies. Then go to the top of L2 and enter the expected frequencies. All right, so let's do that right now, just to get some practice. So here's what I want you to do. Come back here. So for in L1, type 29, 23, 17, and 6. Okay. All right, I'm going to do that in mine. All right, let me know. Well, all right, I'll give you a couple of minutes to get this typed, and then I'll show you what to do next. All right, so once you're there, what you're going to do is this. We're going to hit stat tests. And then the one you're looking for is called, it's D in mine, chi-square, which I can't really type as well here, GOF, for goodness of fit, tests. Test. All right, so try that. And when you get there, it's going to ask you just a few details. It's going to say, well, where did you put your observed data? One. Your expected data, L2. And by the way, in case they're different, you can change these. For example, to enter a 1, you type second followed by 1. And then now here's where it gets interesting. Degrees of freedom. We haven't figured out the degrees of freedom yet. The degrees of freedom is done in the following way. So what do these terms mean? Well, K is the number of columns, or as they're also called, categories, in the table let's call it the observed frequencies table, which in this case is equal to 4. All right, 4. Why? Because if you go back and look, there were 4 columns here. Okay, that's what K means. Now, one we know what one is. M is the number of values estimated from the data. Since we computed lambda from the data, M equals 1. So therefore, the degrees of freedom equals 4 minus 1 minus 1, which is just 2. Great. So, go back to where we left off. I'll just copy these to the next slide. And now we just enter 2 for degrees of freedom. And then you hit calculate. And you'll get everything you need for this test, right? So type them in. L1, L2, degrees of freedom is 2. And you should get, for your test statistic, about 2.00897. And for your p-value, approximately 0.366. That's all. Okay. We could theoretically look up the critical value, but we don't have to, because all we need is this p-value. The p-value lets us know that whether or not we should reject the null. Okay, so if you recall, since the p-value is greater than alpha, we do not reject the null. That data follow Poisson distribution. Okay, So that what we just basically did was show that the data do in fact follow the Poisson distribution. That's what all this work was for. The bottom line is the data do follow the Poisson. And that's all we need to do. Now, again, it is kind of a lot of work, but it's not as bad as it could be because it at least is calculating the test statistic and the p-value for us. If it weren't for that, this would really take a while. So yes, we have to figure out the expected frequencies ourselves, but it's not the worst thing in the world because it's still saving us a lot of time. Wow. So what else could we possibly be asked to do? Well, the other case that we'll want to consider is, our data follow the normal distribution? So you probably calculated normal probabilities more recently than Poisson probabilities. So this will be a little quicker, I think. But the basic process is exactly the same. Now, I do want to mention here that the third part of this chapter may seem complicated when we get to it, but in fact, the calculator will do almost all the work for us. So don't despair. It's not all going to be like this. Okay. All right. So now let's see. What is this all about? We're going to try to find out, a portfolio manager will want to find out if the returns to his portfolio are normal with a mean of 5% and a standard deviation of 10%. So it's just like the one we just did, except that it's normal instead of Poisson. So what data are we given? Okay, so the observed frequencies have to be given to us. We want to know what numbers he actually has in his portfolio. And they're right here. By the way, if you notice, we've broken up the returns into categories like this. They have to be ranges with the normal distribution from -15 to -5%, -5 to 5, 5 to 15, and 15 to 25. These are the frequencies. And if you notice, they add up to 100. Yeah, to 100. So this time the sample size is 100. So what we need to do, again, well, of course, we write out the null and the alternative hypotheses. The null is that the population is indeed normal with a mean of 5% and a standard deviation of 10%. The alternative is that it is not. Is not. That's all we have to choose from. And once again, as we so often do, we'll use the level of significance of 5%. Now, since I am confident that you know how to do normal probabilities, to speed things up a bit here, I will give them to you. I don't think we need practice for this one. So here they are. And if you notice, what I've done is I've calculated the normal probabilities and I've multiplied them by the sample size of 100 to come up with my expected frequencies. But just don't forget, to calculate a normal probability, what you're actually doing is going to second vars and choose number 2 normal CDF. And it needs to know 4 things: the lower limit of your interval, the upper, the mean, and the standard deviation. So this first one, you've got -15%, positive -5%. The mean comes from the null hypothesis of 5%, and the standard deviation is 10%. If you plug those in, you'll see that it is approximately 0.1359. And that's where this comes from. This one comes from. By multiplying it by the sample size of 100, we end up with 1359. We'll do the same thing here, here, and here. Now, of course, just for convenience, we're going to move all that into the table with the observed frequencies. And you'll see this is the result. So guess what we're going to do again? We're going to calculate these from list 1 and list 2. Oh, is that all there is to it? Yes. So again, we could probably use some practice. Why don't you enter those numbers into your lists? And then we're going to run the goodness of fit tests again and see what we get. Right, so you can go back to your list and enter these new numbers, and then we'll run the goodness of fit tests. Let's try that. So when they're done, remember what you're going to do is after you enter them, you hit stat tests. I think it's D. Let me just double check. Yes, it's D. Goodness of fit test. Now, in this case, the degrees of freedom, I'll write it in here. M is 0 because we didn't calculate anything from the data ourselves. K is 4 again. So degrees of freedom is 4 minus 1 minus 0, which is 3. So once you plug those in, and let's see what you get. All right, I'll give you a minute to do this, and then we'll see what we got. All right. So this doesn't take that long. So when you run the test, and by the way, the instructions are in here, and not only that, but so are the instructions for doing this manually. But if you run the test, you'll see that at the end, let me put this in here. Using the TI-84, results are, and so if you do actually run through it, you'll see that your test statistic is about 6.402. And your p-value is 0.09357. So the p-value is, of course, greater than alpha, or the obviously the level of significance. Therefore, we do not reject the null hypothesis. And so we can safely conclude that the data are normal. Or we could say the underlying population is normal with a mean of 5% and a standard deviation of 10%. Okay, so all goodness of fit tests are done the same way. In our case, we'll only focus our attention on the Poisson and the normal. In other words, we're only going to test whether or not the data are normal or Poisson. In principle, you could use any of the others, but we'll stick with just these two. All right, now I'd say that we definitely need a quick break after that, but when we come back, we're going to look at tests of independence where the setup looks terribly complicated, but it turns out that the calculator can actually do a lot of the work for us. Of course, we have to draw the right conclusions from it, but it'll really save us a lot of time. So that's a good way, I think, to wrap up the evening with a relatively simple case. And when that's done, we're done with chapter 13, which is good because the final exam will be on 13 and 15 only. So of course, with a once a week class, you have to worry that, run out of time. I think we're in pretty good shape now. So once you take about 15, 20 minutes, and come back at about, let's say 8:25, and then we'll pick it up from there. In the meantime, I'm going to pause the recording so that we don't have 20 minutes of dead time here. Let's see, how do I do this? There it is. All right, so see you in a while. All right, so now we're ready for our last section of chapter 13, which is our discussion about, let me get it open and show you. Let's see. Oh, they're here somewhere. There it is. All right, so this time we're going to be testing hypotheses about the independence of variables in a data set. Okay, so whatever variables we're studying, we may want to know if they're independent of each other or not. So this one will be set up in a very similar way to some of the other ones we've been looking at. The null will be that the variables of interest are independent of each other. The alternative will be that they're not. So once again, it's a right tail test. Now, how does this work? Well, let's just look at an example. Imagine that Starbucks is trying to know if men and women tend to prefer the same styles of coffee. So the variables of interest are the coffee flavor that people prefer and gender. And we want to know if they're independent or not. So we choose a sample of 100 men and 150 women, and we ask them which is their favorite flavor. So the following table, which is known as a contingency table, shows us what we need to know. So you see here, we've got, instead of just a single row of observed values, we have two rows, an entire table. And so men and women are broken down, and we see that we listed them by whether they prefer Komodo dragon, French roast, or Sumatra. So these are the totals down here. We want to know if the proportion of men who like Komodo dragon, French roast, and Sumatra is the same as it is for the women. Now, the test statistic for this type of situation is actually pretty terrifying to look at. It is very time consuming, or it would be if we didn't have a special ally in our calculators, because the calculators can do this in a very quick and simple way. So let's just say that first things first, the null hypothesis, as we've already seen, is here. The variables, in this case, the coffee preferences and the genders, are independent of each other. The alternative is that they're not. Let's say that the alpha is 0.05, as it so often is. This is what we want to focus our attention on. Now, just like with the goodness of fit test, we need to supply the expected frequencies. Once those are done, then you could compare the observed with the expected frequencies and come up with a test statistic, which we then compare to a critical value chosen from the chi-square distribution. But the calculator makes this unnecessary. Let me show you exactly how this works. So let's see, I'm going to find a convenient place to put this. Yeah, so in the notes, everything's being done by hand. But what I'm going to do is show you instead, I might as well stick it down here, how to do the same test with the TI-84. So you'll be very happy to see how quick and easy this is. All right, so what you're going to do is this. We're actually going to use a completely new feature that we've never seen before. The test of independence can be implemented with the TI-84 by entering the observed data into a matrix. Okay, now, what exactly is a matrix? Well, oh, I forgot. What did I do? You may have run into this in a lower level math class. Let me just run through a quick example. You may remember solving equations like something like this. Here we have a system with simultaneous equations, and one technique for solving for X and Y is to set these up as a matrix. And if this doesn't look familiar to you, that's okay. This is a matrix which contains the coefficients of X and Y. And we notice that it has two rows and two columns. And so its dimensions are said to be 2 by 2, 2 rows, 2 columns. Fine. So a matrix is simply a way of storing information. What we're going to do is enter the observed frequencies into a matrix in this calculator. The question is how. All right. So what we're going to do is this. To enter the data into a matrix, that's what we have to do. Second, now for this one, it's not second vars, it's second, and then there's a button here which you may not have noticed before, X inverse. It's slightly, you might, if you look at sort of towards the middle of the first column of buttons, it's very close to the sign button. And if you notice directly above this button, X inverse, it has tiny little letters where it spells out the word matrix. So if you choose it, you'll have a lot of information there. What you're going to do is go across with your arrow key and choose edit. Okay. When you do that, hit enter. And then what you'll see is it says matrix A, and it wants to know what dimensions you need. So let's go back and revisit the data for our observed frequencies. Aha. Wait, let's go back. So excluding the totals, we have 2 rows, one for men and one for women, and 3 columns, one for each style of coffee. So that means that our dimensions are 2 rows and 3 columns. So what you're going to do, if it doesn't already say so, you have to change the dimensions to 2 by 3. And the way to do that is to actually just type over it. That's all you have to do. And you'll notice there's a huge matrix underneath that name matrix A. Those cells are designed for you to enter your data. So what you're going to do is type it in. Oh yeah, look at that. It's not a coincidence. It's giving you room for all 6 elements of our observed frequencies. And that's because you asked for a 2 by 3 matrix, 2 rows, 3 columns. Okay, so you're going to enter them. And in fact, oh boy, hold on a second. I don't want to keep scrolling back and forth. Oh, here we go. It's 30, 40. 40, 80. And here it is, 30, 30. So literally all you have to do is enter those numbers. All right, so let me leave it there so you can see. Go ahead, enter those numbers into matrix A. Right, 30, 40. 40 and 80. 30 and 30. Okay, so I'll give you a minute to catch up and then we'll see what comes next. And you'll be very pleasantly surprised by what it's capable of doing. All right, so I think, let's see, if you're done, you're going to hit now you're going to hit stat tests. And this time you're going to choose, it should be C, which stands for chi-squared test. That's all it says, chi-squared test. And when you get there, it's going to say the following. Observed A, expected B. If it says that, go ahead and hit the calculate button. If not, you'll have to change the matrices. But those are the settings that it comes with from the factory. So it should say A and B. And what you're going to do then is just go down and hit calculate. And by some miracle, it's going to come back and give us everything we need to know. Namely, the test statistic and the p-value. So the test statistic is 4.96. The p-value is 0.083729 something. Which, as you know, because the p-value is greater than alpha, that tells us not to reject the null hypothesis. That gender and coffee preferences are independent. Okay, so what that means then is that we've shown that men and women basically like the flavors equally. Okay, or think about it this way, the same proportion of men and women like the Komodo dragon and the other two flavors. So we have shown that there is no evidence to suggest that there is a relationship between gender and coffee preferences. Okay, now here's an interesting twist. If you look in the slides, you'll see that we went through a lot of trouble to figure out the expected frequencies, okay, like we did with goodness of fit. And in fact, I'm going to show it to you right now. All the gruesome steps are in there. Everything that was done to get to these numbers is listed in the slides. So it turns out that the calculator has actually done this for us. So if you want to see the results, to see the expected frequencies, what you're going to do is hit second X inverse, meaning you're going back to the matrices. Oh my God, it's been very stubborn with me tonight with the superscripts and subscripts, let me tell you. Okay. I don't think it worked. Okay. And then you're going to say, go down to B. This thing is just unbelievable. Might be nice if it obeyed me. So B. So go to B, hit enter twice. And what you're going to see is the contents of matrix B, and you'll see it is exactly what you saw up here. (28, 48, 30, 24 in the first row, 42, 72, and 36 in the second row. So in other words, it did that for us. This shows the matrix meaning the expected frequencies. So if you need them for some reason, they're right there. Okay, that's the part that it saved us from doing. It would have been nice if it could have done this with the goodness of fit test, but we weren't quite that lucky. But here, it's taking care of it for us. So in effect, the calculator is essentially doing all the tedious calculations for us and leaving us to draw conclusions from it. And that's kind of nice. So you can see that the first set of problems we did with the population variances, the calculator essentially did none of the work for us. With the goodness of fit tests, it did some of the work. It was at least able to do the test statistic once we calculated all the expected frequencies. And then here, for all practical purposes, it's doing everything for us, and that we just have to draw the conclusions. So the calculator can do a lot of chi-square applications, just not all of them. It isn't quite that advanced. Possibly one of the more advanced TIs can do that, but for our purposes, this is how you'll solve for all these different types of problems. So those are the three that we wanted to cover here. We know the properties of the chi-square distribution. We know how to test hypotheses about the population variance. We know how to conduct goodness of fit tests, and we now know how to conduct independence tests. Wow, that's a lot for one night. It really was a very intensive cram session, but we have to do this because the final exam is going to be based on 13 and 15. Now, 15 is even more involved, but at least there we can get some help from the calculator. And I can also show you how to implement the material from chapter 15 in Microsoft Excel. Okay, now everybody will benefit from having more Excel skills. That's just the bottom line. All right, so we'll do that next week when we meet on the next Tuesday, and we'll carry on from where we left off here. Maybe we'll go back and quickly review what we did tonight, but we want to focus next week on chapter 15, which is our introduction to regression analysis. Okay, and again, it's something that's going to seem complicated at first, but in reality, once we realize that the calculator can help us with it, you'll see that it isn't really quite that bad. Okay, so anyway, since it is just before Thanksgiving, I think we've done plenty of work for one night, and I think we should knock it off right here. And then I'll just see you all next week again at our normal time and place. All right, how does that sound? Pretty good. So we'll wrap it up right here, and I'll see you all next week.